This is a lecture on sampling distributions and the idea of the central limit theorem, one of the very important theorem in statistics. All right, what is assembling distributions? Before we can talk about assembling distributions, we need to introduce the idea, the definitions of a sample statistic. So a sample statistics is a characteristic, right, that is formed when random samples of size n are repeatedly taken from a populations. What does it mean? If imagine I have a populations here, right? And then I randomly taking random sample from this populations of size n. So this is a sample of size n. And then from the sample, for example, if I want to find the sample means of my sampling distributions, I take the mean of this sample. I call it x bar 1. So x bar 1 is a sample mean of the first sample. And then I take another sample of size n, right, the same size, and I find another mean of the second sample, and so on and so forth. So I repeatedly taking random samples of the same size, and I've calculate the mean of each of the sample, right? So I'm gonna have a bunch of them. All right. And then the sampling distributions of the sample means, right, is the distributions of all the means that I calculate from each of the sample that I collected. Okay, again, the distributions of the sample means is a sample statistic, which is the sample mean. That means from all of these sample means here, I can create a distribution for all the sample means that I collected from all the samples, from all the random samples of the same size. Okay. So if I have a distributions and I put all the sample means in this distributions, and from this distributions, I have a sampling distributions of the sample means, right? And then here is the, and the mean of this distribution should be the mean of the sampling distributions of the sample means. So I would say the mu, right, is a mean, but then of the sample means. Okay. And then if once I have all the samples that I collected, I can, in each sample also, I can calculate standard deviations, right? And the distributions, this is the distributions of the sample means that I collected from my samples. I found the mean of this distributions, that also I can find the standard deviations of these distributions. All right, this is an examples of the sampling distributions of sample means. Again, you forming a distribution for all the sample means, right? All the means from your samples. And again, those samples are random samples of the same size n. All of the samples here have the same size, which is n. Now, I will introduce a simulations that will help us imagines how sampling distributions related to the distributions of the populations. All right, this is a simulations of assembling distributions, at first I want to use the right scale distributions for my populations, and I want to find the mean, right? We go here. As you can see, it's here. This distributions here is the distributions of the populations. Okay, and then if from this populations, I would take a few sample size, right? A few samples, random samples of size 2, let's say size 2. And then if I take 5 random samples, I will have a distributions. If I take 5 random samples here, ask me to do it again. All right, so right scale, compute. Okay, again, this is the sample, this is the distributions of the populations, right? And then if I'm taking random samples of size 2, if I take 1 samples and I find the mean of that samples. So the second chart here will tell you the populations, the 2 observations from the populations, and the last chart here will tell you the mean of the sample that I just took. Okay. How about if I do it 5 times? Like I want to take 5 random samples of sample size of 2. So that's the first one, right? The first mean and the second mean that I get from the second samples. Then the third one. And then the fourth one. The fifth one, right? As you can see that, look at the last charts here. This is the sampling distributions of the sample means from those samples that I took from the populations, okay? What about if I do it 1,000 times? If I 1,000 times is mean I took 1,000 random samples from the populations of size 2, and the last chart here again is the sampling distributions of the sample mean. Now we want to look at the mean of the populations. When we started is about 14. The mean of the sampling distributions of the sample means is about the same, which is 14. Okay. How about the standard deviations of the populations is about 11.8, and the standard deviations of the sampling distributions of the sample means here is about 8.179. So the standard deviation is smaller. That means the variations of the sampling means is smaller compared to the variations of the populations. So this is an illustration of a skill-right distributions when the sample size is 2. What if I get a bigger sample size to see if it's changed? So I just want to have sample size for all my samples is about 30. Okay. And then I'll run it 1,000 times. See what happens. What happens is you have the same population distributions, but your sample means change. How does it change? It changed from a little skill right distribution to a symmetric distributions or a bell-shaped curve distributions here. And if we look at the mean of the distributions of the populations is still the same as the mean of the sampling distributions of the sample mean. It's around 14, right? The standard deviations of the sample means is much smaller. As you can see that the distributions of the sample means here is much skinnier. So as we increase the size of the samples that you're taking from the populations, the distributions of the sample means is approaching to the normal distributions. And the mean of the sampling means is the same as the mean of the populations, and the standard deviations of the sampling means is much smaller compared to the standard deviations of the populations. So from this simulations, you can see that in order to estimate the mean of the populations, you can find like 1,000 samples, right, of the sample size, of the same sample size from the populations, and you can calculate the mean of those samples. And then you can create a distribution of the sample means to estimate the mean of the populations because they're pretty much the same. Now, what if I change the distributions of the populations to be bell-shaped distributions? And then I do the same simulations to see what happens to the distributions of the sample means. Another one. So I changed to bell-shaped, right? The mean is 25, the standard deviation is 5. I compute it. So as you see that the distributions of the population is first appear to be the bell-shaped curve, normal distributions. And then if the sample size is 2, if I run it 1,000 times, the distribution of the sample means is also a bell-shaped curve distributions with the mean of the sample means is the same as the mean of the populations. And also the standard deviation is still quite smaller compared to the standard deviation of the populations when the sample size is 2. Okay. What if I increase the sample size to 30? And I run it 1,000 times. I get a different distribution for the sample means. I have the same shape, right? It's still pretty much like bell-shaped curve, but the standard deviation is much smaller, which is 0.9 compared to 5. So the variations of the sample means distributions is much smaller compared to the variations of the population. And you can see that if you increase the size of the samples, the variations or the standard deviations of the sampling distributions decreases. And how do the standard deviations of the populations and the standard deviation of the sampling means related? They are related by a factor of square root of the sample size. And the simulations, simulation that we just did kind of introduces us to the central limit theorem, but one of the very important theorem in statistics. So the central limit theorem talks about the relations between the mean and the standard deviations of the populations and the sampling distributions. Okay, it says, if the population is normally distributed, the sampling distributions of sample means approximates a normal distributions, which is what we just saw, right? So if the population is normally distributed, the population mean here, the sampling distributions of the sample means is approximates a normal distributions. Okay. And then if a random sample size n, where n is at least 30, where the sample size is at least 30, or draw from any populations any shape of the distributions of the populations with a mean and a standard deviation sigma, then the sampling distributions of sample means approximates a normal distributions. Also, the mean of the sampling means is the same as the mean of the populations. Okay. The standard deviations of the sampling distributions of the sample means equals to the standard deviations of the populations divided by square root of the sample size. And if you want to talk about the variance, so the variance of the sampling distributions of the sample means is the same as the variance of the populations divided by n. So these are the relations between the population distributions with the sampling distributions with regard to the sample size. So it is saying if you have a populations that is a normal distributions, right? X. Then the distributions of the sampling distributions for, let's say, of the sample means is also normal distributions. Okay. And you have that sigma here is the same as sigma x bar. Okay. But then if you start, so this is the populations. And this is the sampling distributions. Okay. And then if your population distribution is not normal, let's say it's skew right, then if n equals to, n is at least 30, then the distributions of the sampling distributions is also approximates a normal distributions. And also sigma here is always as the same as sigma divided by n. And then sigma is the standard deviations of the populations. Okay, and we know that the sampling the mean of the sampling distributions is the same as the mean of the populations. Okay. One thing that you want to keep in mind is if your population is normally distributed, then it doesn't matter what is the size of the sample. The sampling distributions is always approximates a normal distributions. Okay, and say any sample size. Okay, but if you have a non-normal distributions for the populations, then in order for the sampling distribution to be normally distributed, the sample size has to be at least 30. Let's look at the next example, example number 9, salaries, right? The annual salary for a clinical pharmacist is normally distributed with a mean of $111,000 and the standard deviations of about $13,000. Random samples of 48, right, are drawn from these populations and the mean of each sample is determined. Okay, so you draw 48 you draw a lot of samples of size 48 from these populations, and the populations is the annual salary for clinical pharmacist. And then you determine the mean of each sample. So the question is, find the mean of the sampling distributions of the sample means. So the mean of the sampling distributions of the sample mean sigma x bar is the same as the mean of the populations because n equals to 48. And then you can use the central limit theorem, right? To determine the mean of the sampling distributions. And in fact, the mean of the sampling distributions is $111,000. And the next question is, find the standard deviations of the sampling distribution of the sample means. Again, because n is 48, you can use the central limit theorem. Then you know that the standard deviations of the sampling distributions of the sample mean equals to the standard deviation of the populations and divided by square root of n. And we know that the standard deviation of the populations is 30,000 and n is 48, so divided by square root of 48. Okay, which will give you is approximately about $86.39. Okay, now I can use the mean of the sampling distributions and the standard deviation of the sampling distribution to graph the sampling to sketch a graph of the sampling distributions. So the sketch of the graph is here. And by the central limit theorem, n is 48, right? Then the shape is normal distributions. Right. So you have normal distributions here. You know the mean is still is determined and is $111,000, and the standard deviations is about $1,876.39. So this is the sampling distributions of the sample means of samples of size 48 that you drew from the populations of annual salary for clinical pharmacists. Now let's do the next example. Finding probabilities and using the central limit theorem in order to determine probabilities and the values of sampling distributions. All right, so carbon dioxide emissions, the per capita carbon dioxide emissions in 58 industrialized countries over a 22-year period is about 25.5 metric tons. So you know that this is the mean, right? In 58 industrialized country. So this is the population, 58 industrialized countries is the populations. It's a population size, okay? And then you find the mean of the populations is 25.5. A random sample of 44 countries, that means n is 44, is selected. What is the probability that the mean carbon dioxide emissions for the sample is greater than 28 metric tons? Assume that sigma is 395.1 metric ton. Okay. So you're asked to find the probability of the mean of the sample. That means you need to look at the sampling distributions of the sample means, right? if you want to look at the sampling distributions of the sample mean, since n is greater than or at least 30, then the sampling distributions of the sample mean is a normal distributions. And if it's normal distributions, and we know that the mean of this sampling distributions is 25.5, which is because it's the same as the mean of the populations. Okay, and then we can figure the standard deviations of the sampling distributions by taking the standard deviation of the population divided by n, which is 395.1 divided by square root of 44. So sigma x bar equals to 59.56. Okay. And then we want to find the probabilities of the mean of this sample is greater than 28 metric tons. That means my interest values is 28, and 28 is on the right of the mean. And I want to find the probabilities of the mean that is greater, so that means I need to find the probability to the right of this point, right? So I would say the x bar is 28. Okay. All right. Now the probabilities is, say, the probabilities of the x bar of the mean of this sample is greater than 28 is the same as the probabilities of 1, right? 1 minus the probabilities of the x bar of the samples of size 44 is less than 28 and is equals to, and then I can find z values, right, for x bar. And what is a z value? I haven't found it yet, because here, if the distributions is normal, then you can use a z value and z table to find the probability for this x bar here. We know that the x bar is 28. The x bar, the interest value is 28. That means the z value of this x bar is 28 minus 25.5 divided by this standard deviation, which is 59.56, equals to 0.04. Okay, 0.04 is a z value, and I can plug 0.04 into here. And then I can go to my z table to find the probability to the left of 0.04, which is 0.04, 0.51595. And thus we give you 0.48405, which is the probabilities of the mean, right, of the sample of this 44 countries here would have the carbon dioxide emissions is greater than 28 is about 48.4%, right? If you pick, that means if you pick a random 44 countries and you calculate the mean of the carbon dioxide emissions from those 44 countries, and the probabilities of the mean of that sample is greater than 28 metric tons, is about 48%. This is what it is about. One thing that you want to keep in mind is if you want to find the probabilities that related to the sample mean, you need to use the sampling distributions of the sample mean, right? And this is the sampling distribution of the sample mean here. Now look at the next example. So the lengths of lumber a machine cuts are normally distributed with a mean of 96 inches and a standard deviations of 0.5 inches. Okay. What does it tell you? It tells you that if you use a machine, right, to cut lumbers, the length of each lumbers or of all the lumbers are normally distributed. That means you can use a bell-shaped curve for the distributions of the lengths of all the lumbers that are cut by this machine. And the mean of the populations is 96 inches and the standard deviations is 0.5 inch. So the question is, what is the probability that a randomly selected bore cut by the machine has a length greater than 96.25 inches? That means if you just randomly pick a bore, right, from all of these bores that are cut by this machine, what is the probability that the bore that you just picked that has length is greater than 96.25? Okay, so my interest value is 96.25. I say it x1. Okay, and I want to find the probability to the right of this value. So P of x greater than 26.25 equals to P of, because it's normally distributed, I can use a z-table. And in order to use a z-table, I need to find the z value. So what is the z value of this x? So the z value here is going to be 96.25 minus 96 divided by sigma, which is 0.5. You get 0.5 is a z value. So z greater than 0.5. So it's the same as 1 minus p of z is less than 0.5. And then you can use a z-table to find the probability for z equals to 0.5. 0.50 is going to be 0.69146. And then you can do these calculations. All right, so what does it mean? That means if you randomly pick a bore, then the probability of the length of this bore would be greater than 96.25 inches is about 30%, right? 30.8%. Well, the next question is, if you randomly select 40 bores, what is the probability that the mean length is greater than 96.25 inches? Again, you're not picking one bore, you're picking 40 bores, and you find the mean length of those 40 bores. So then the question is, what is the probability that the mean length of those 40 bores is going to be greater than 96.25 inches? So if you're taking 40 bores, that means the sample size n is 40 and it's at least 30. So then you can use the central limit theorem, right? And the central limit theorem say the sampling distributions of the samples gonna be normal with the mean of the sampling distribution is the same as the mean of the populations. But the standard deviations of the sampling distribution has to be equal to the standard deviation of the populations divided by square root of n, which is 0.5 divided by square root of 40, which is 0.08. I rounded up, okay. So the sigma of the sampling distribution is 0.08, and my point of interest is still 96.5, right? 96.5 now is not value, it should be a sample means, right? 96.5. I mean, you take all the samples, right, of the same size. What is the mean length of the sample that is greater than 96.25? And again, I want to find the area to the right. Okay. First, again, I need to find the z values because the sampling distribution now is normal, so I can use the z value. And the z values is going to be calculated using this same formula, right? Equals to 96.25 minus 96 still, divided by this standard deviations. It's going to give you 3.125. You have a huge z value compared to the z value up here. Okay. Then you can find the probability of the x bar, right? It's going to be greater than 96.25. Is the same as the probability of x bar of 1 minus the probabilities of x bar less than 96.25 equals to 1 minus the probabilities of the z value that is less than 3.145, and I just need to use a z table to find that. 3.125, I rounded to 3.13. So 3.13, 3.13, which is here 0.999913. 1 minus 99913, which will give you 0.0087. Okay. What does that mean? That means if you pick 40 bores and you find the mean length of those 40 bores, then the mean length of those 40 bores, the probabilities of the mean length of those 40 bores that is greater than 96.25 will be very, very small. A very small chance that you're gonna pick 40 bores that has a mean length that is greater than 96.25. And the chances are about almost zero, right? 0.00087. Okay. So this is how you use, how you approach the sampling distributions, how you construct the sampling distributions, how you analyze the mean of the sampling distributions, right? The mean of the sample means, and how you compare the mean of the sample means with the mean of the populations and the standard deviations of the sample means with the standard deviation of the populations. And if the sample size is big enough, which is at least 30, then you can use normal distributions for the sampling means distributions. If the size is less than 30, then you have to look at the distributions of your populations. So if the distribution of the population is normal, then regardless the size of the samples, the sampling distributions is always normal. But if the distributions of the population is skew right, skew left, or non-normal distributions, and then the size of the samples is less than 30, then the sampling distributions is not going to be normal.